As we start every chapter, we're going to go back and look at what is meant by Okay, as we start every chapter, we're going to start this one. We always go back and look at where we've been and where we're going, right? Remember we started the textbook out with materials. And then we said in order to understand materials, we're going to have to understand atoms and molecules. Then we said, what do atoms and molecules do? Okay, remember that? Then we studied a particular kind of a weird state. Or phase called gases. Okay, and I think I said to you, why do we have this here? I don't know. And then we went back to the story, why do atoms do what they do? Why do they, right? We said, what do they in chapter 4? We said, why do they in chapter 6? And now we're going to go back actually to energy. And we're going to look more specifically, not just at atoms and molecules, really more at atomic structure. Okay? Now, in order to understand atomic structure, we have to appreciate a few things. And I want to first of all call your attention to an old friend of mine, Erwin Schrodinger. He's been gone a while, but Erwin Schrodinger is a central figure in the story of the structure of atoms. And it turns out that he and a few other very clever scientists put the powers of their interest and their focus into studying what happens with atoms and what happens with electrons. And they found at around the turn of the century, and that is the last century, not this one, so around 1900, 1905, 1910, and we're figuring out that that things don't, that things at that size scale don't act the same as things where you and I live, right? So if you throw a ball across the room, you can say some things about how it travels across the room and such. And it turns out electrons cannot be described in the same way. And so they introduced a new field of physics called quantum mechanics. Now, it's important to appreciate that very little things, and when we say very little, Tro uses the term absolutely little, and I think it's a good one. Absolutely little. That is, absolutely little things exist in discrete states and not continuous states. All right? And what that means is, well, by his use of the word absolutely means nothing smaller. This is so small that the idea of size begins to break down. All right? So how big is an electron, for example? It turns out it's really difficult to describe its size. Not because we don't have calipers small enough, but because the meaning of size breaks down when you get this small. Okay? And there's a few other things that break down too. So I use the term here, Tro uses it, everybody uses it, the term discrete and not continuous, okay? So let me just give you briefly, let me say something about this, that if you throw a ball across the room, you might say that the ball is here, and then the ball might be here, like we're throwing it that direction, okay? And then it might be here, but there was a time at which it was in between, right? And there was a time that was maybe here. And there was another time in which it was here. And there was another time in which it was here, right? And I could pick any point along here and say the ball was there at one point, okay? And so the ball is going to keep going. And we know that at some point the ball was here, at one point it was here, one point it was here. We could choose any path along this trajectory and say that the ball was there in between those, okay? And so we would say that that path was continuous, okay? Now, an electron doesn't do that. An electron, when it travels in some paths, okay, so bear with me. If you're a physicist, please don't criticize my explanation here. I want to start out with something very accessible and say that electrons, when they're traveling, they go from, this is a ball, okay, let's go here. A ball, how do you spell electrons? A little special E there. Electrons, if it goes from here to here, it never exists in between. Okay? It's like a flash photography. The electron is first here. Position 1. Position 3. Wow. A couple extra letters in there. Position 3. Okay, and it never exists in between. It's going to be in position 2, position 1, 2, 3, and 4, and 5, and so on. But the electron never was there. What? It never was there. Okay? So that's what we mean by discrete states. All right? And we'll talk more about discrete states. Now, I strongly encourage you, please pause this video and look up. Pause the video that you're watching me and look up this video, and I'll try to put that link on YouTube so that you can just click on it. But if you can't just click on this link right here, pause the video and look at it. Okay, so let me suppose that you did, and let me suppose that you did look at it, and let me say you can see how guitar strings, they cannot have an odd number or just any old random number of modes, right? They're either going to, or waves, I should say. They can't have, 1.13 waves in them, right? They either have a half a wave, or 2 halves of waves, or 3 half waves, or 4 half waves, right? But you can't have, 2.68 times 10 to the 4 waves. You can't. Well, that you could, because that was an even number, but you couldn't have 2.68 waves, right? That you can't have. So, all right, now that we know we've defined discrete, I'm telling you we're going to have to practice this a little bit. If you don't like it yet, that's normal. It's not. I wouldn't like it either. So we've defined discrete and continuous. You've seen discrete before. Please go look at that video. Let me say now, electrons are absolutely little. So they are going to obey quantum mechanics, okay? So in the realm of quantum mechanics, electrons are. And we have to use quantum mechanics to describe how electrons act, all right? And there are other things, which I don't want to tell you right now. Just want to really focus on electrons right now. Other things are also absolutely little. So there's a few things that are going to have to be described by quantum mechanics and will not be sufficiently described by classical mechanics, okay? Now, here's a weird thing. Ready for this? Very small things can exist in more than one state at once. All right, so by state, let me suppose that if we're talking about the temperature of a cup of water, it might be, say, 4 degrees. And if it was discrete, we might find that the temperature could also be 10 degrees, right? But it might not be able to be, say, 6 or 5, okay? Suppose these are 2 possible states. And I'm saying suppose, okay? Possible states of a cup of water, right? Temperature is 4 degrees, temperature is 10 degrees. Suppose that those are the possible states, okay? Now, it turns out that if a cup was very small, like absolutely small, then we would say that it could exist in more than one state at once. It could be 4 degrees and 10 degrees, all right? And that makes no sense in the macro world. It makes no sense at all. Matter of fact, even as we try to understand it in the micro world or the sub-micro world, it makes no sense at all. But it turns out that there are important experiments that have been done to verify this, but it makes absolutely no sense. Read that again. If you believe me, you did not read it right. Read that again. If you believe me, you didn't read it right. It's bizarre. Can you see it? Very small things can exist in more than one state at once, okay? And I think it's funny that Erwin Schrodinger said, I don't like it, and I'm sorry that I ever had anything to do with it. I don't like it, and I'm sorry I ever had anything to do with it. Amazing, right? So he's one of the, I would say important scientists who gave us this quantum mechanics, gave us this theory. All right, and so we'll close with the story about Schrodinger's cat. So Schrodinger's cat is a story that, it was just a thought experiment that Schrodinger made up about a box, and inside the box was a cat, okay? And so it turns out that the cat is inside the box, and you have this electron which is in this box over here. Can you see a little box for an electron? So inside that box is an electron. Now, if the electron flips, okay, or goes from one state to the other, then it sets off a little hammer. The hammer comes down and breaks the vial. Can you see that little hammer right there coming down and breaking that vial? Inside the vial is poisonous gas, and the poisonous gas poisons the cat, and the cat dies. Schrodinger said that, I'm sorry, there's one more thing I got to tell you, that it's the very small things can exist in two states at once, but watch this now, the act of observation forces object into one state or the other. So, in the cup of water analogy, you've got a cup of water that is in both 4 degrees and 10 degrees at the same time, but when we measure it, it's only 4 or it's only 10. Okay, so the measurement itself, or what Tro calls observation, the measurement itself forces the object into a particular state. Okay, now let's go back to Schrodinger's cat. So you got this electron, it's in a box, and if the electron flips, then a hammer comes down, breaks the vial, gas goes into it's cyanide gas, okay, and so the cat dies. Well, before we open up the box and look inside, Schrodinger claimed that the electron was both flipped and not flipped. Do you understand what I'm saying? If you believe it, you don't understand it. All right, it's bizarre. The electron was both flipped and not flipped. And so, since it was flipped and not flipped, the hammer was both back and the vial was intact, and the gas was inside the vial and the cat was alive, and the hammer was down and the vial was broken and the gas was inside the box and the cat was dead. So the cat was alive and dead at the same time. Now, I'm going to say something that I've never heard any of the scientists say. I don't believe it. And I have the secret to Schrodinger's cat. Now, this stumped Einstein and Heisenberg and Dirac and Schrodinger. It stumped them all. They were morons. I have the answer. And if you want the answer, you need to come to class. See you there.